We're looking at 5 ways to find exoplanets. We've already looked at 4. Today we're going to look at the 5th. But what are those first 4? Well, we can take a photo of them by covering up the host star. We can look for the bending of light rays as they pass near massive planets. We can look for the wobble of a planet when we compare it to other stars up in the sky. We can look for the wobble of a planet where it's coming towards us and then away from us, and we can detect that through the Doppler effect. And now for the 5th and most common way to find exoplanets. First, I would like you to write down in your science journal what you think this is a photo of. And then I would like you to read this article before you go any farther. Make sure that you can answer this question: who is Jeremiah Horrocks and what did he do? After reading that, you probably should have a good idea of what this is. This is actually a transit of the planet Venus across the surface of the sun. These are his actual observations that he drew back in 1639. He didn't actually stare at the sun to do this. He had the sun go through a telescope, projected that onto a wall, and then was able to trace the transit of Venus, very similar to how Galileo first was able to record sunspots. A little over 100 years later, Captain Cook was able to do the same thing from Tahiti. He actually brought down a tent where he was able to block out all of the light so that the only light coming in was the light coming in through his telescope. When Venus goes in between us and the sun, that is known as a transit of Venus. And they occur in pairs, but those pairs happen with like 100 years, or a little more than 100 years in between them. There's only been 53 transits of Venus visible from Earth since the year 2000, and only 6 of them visible since we invented telescopes. The last one to happen was in 2012, but don't worry because the next one is in 2117. Definitely taking my astronomy class outside to see that when it happens. But back in 2012, there was a lot of really cool photos that were taken. Here's cute little Venus in front of the surface of the sun. Planets are not the only thing that can transit. This is actually the space station transiting across the surface of the sun. Here is another photo of the space station with a shuttle about to dock, transiting between us and the sun. Here we have the space station as well as Venus, both transiting the sun at the same time. And this is the space station transiting between us and the moon. So as long as you have one object blocking a little bit of another, that's known as a transit. You can see that if you speed time up quite a bit, little Venus is just going to cruise across the surface of the sun. It's not extraordinarily breathtaking, but it's kind of cool to see a little planet travel across. I'd like you guys to draw this graph 3 times in your science journal. Brightness on the y-axis, time on the x-axis. Imagine that you have a light sensor, and that light sensor is aimed at a lamp. I want you to draw what you think that line would look like. What would the graph of the brightness over time look like? Go. Hopefully, you came up with something like this. Let's take a look at that actually happening. If you have a light source, in this case a flashlight, and a light detector, in this case my phone, and you are simply shining light into a light detector, you should see a pretty straight line as there's no change in the amount of light coming out of the light source into the detector. Now I want you to imagine that there is an object that goes between the light and the light sensor, an object like a book. I want you to predict what that graph would look like. Hopefully you guys came up with something like this. Let's watch that happen. If we pass a book, in this case Carl Sagan's Cosmos, in between the light source and the detector, let's see what happens. Pretty obvious that the book is blocking the light from the light source, getting to the detector, and your graph of the amount of light going into the detector goes all the way down to 0. Now imagine that instead of a book going in front of a light, it's a planet going in front of a star. Graph what you think that might look like. Let's watch that happen.
Let's use our imaginations. Instead of a flashlight and a phone and a book, we are going to have a star, a telescope, and a planet. As the planet is orbiting around the star, it's going to come in between the star and the telescope. Let's see what happens. Turns out the planet is also able to block some of the starlight from getting to the telescope.
What you get is what's known as a light curve, where you have an amount of light that changes and then it's repeated because a planet is blocking the light from that star. Here's a question for you. What does the depth of the dip tell us about the planet going in front of the star? Let's find out.
Let's use a smaller planet orbiting the same star. Let's see what happens.
What did you notice when you saw the large planet versus the small planet? And what does the time between those dips tell us about the planet? Let's find out.
And what if we have a planet that is orbiting farther away, so it's going much slower? Let's see what happens.
Think about the difference between when you saw a planet go fast versus when you saw the planet orbit more slowly. How did that change the graph? And then answer this question. What does the interval between the dips tell us about that planet? So the depth of those dips tells us the size of the planet, and the amount of time that elapses in between tells us the orbital period of that planet. If we know the orbital period, can we figure anything else out? Is there any sort of equation that we've looked at this year that tells us if we know the orbital period, we can figure something else out? Kepler's third law actually tells us that if we know the orbital period, we can figure out how far away that planet is from the star. Which means, from just this light curve, we can tell how big the planet is, we can tell its orbital period, and we can tell how far away from the star that planet is. What we're going to look at for the next couple days are known as transit light curves. Here are a couple of transit light curves of actual exoplanets that exist up in space that NASA has found. And you'll notice that the light curves are different sizes, and that corresponds to a couple things. The planets are different sizes, but the stars are different sizes as well. So if you have a big planet in front of a small star, you're going to get a pretty large dip. But if you have a big planet in front of a bigger star, that dip's not going to go down as far. This planet is actually bigger than that planet, but this planet is causing the dip to go down much farther. Why? Because it's covering a larger proportion of that star than this one is. What you would see if you worked for NASA is something that looks like this. It's a big jumble, but you can tell that there are dips that are very regular, that repeat themselves. When you zoom in, you'll notice that the measurements are kind of scattered, and that's simply because they're so far away. What they do is fit a best fit line through that data, and they are able to then figure out how far down that dip goes and how often that happens. I just want you to know that they are not nice and neat like that necessarily. They do have a little bit of a scatter, but it's very, very easy to tell that there is a dip right there in the data. So the fifth way that we find exoplanets is known as the transit method. When a planet passes directly between us and the star, it's going to block a little bit of the star's light, and it's going to cause there to be a dip in what we call a light curve. Go ahead and write that down. Now I'm going to have a few questions for you guys. I want to see how you guys do. We have two identical stars, each with their own planet, but the planets are different sizes. Now before those planets cross in front of the star, I want you to predict how those two light curves are going to be different. Now let's watch. The light curve of the larger planet dipped down much more than the light curve of the smaller planet, because the bigger planet blocked more light. Now we have a star with three different planets. Each one of those planets is a different size. Let's see what happens as those three planets cross between us and the star. We'll start with the biggest planet, and that's going to cross, causing the light to dip, and then it leaves from between us and the star, and we have the second planet that is going to cause the light to dip. You'll notice, though, that it doesn't dip as much, and that's because this planet is not as big. What do you think is going to happen when this little planet then crosses between us and the star? Let's find out. This light curve actually dips down farther because it had two planets. When the medium planet left, now the only thing in between us and that star is the smallest planet. And so you get a light curve that looks like this. And you guys will eventually be able to read there's one big planet, and then a second smaller planet, and then a third planet causing there to be a dip. The key is to look at how much that line changes, and that will tell you the difference in the planet sizes. Here's another question for you. What does the slope of the line tell us? Watch what happens as this planet is leaving from between us and the star. As it is leaving, that is the slope. So while it is not completely covering, but covering a little bit, that's going to be where the line slopes. So what do you think the slope of the line could tell us? It tells us the planet's diameter. The craziest thing is that we are probably missing most planets that exist. Here's why. As we look at distant stars, we're going to zoom in on them, and we need to have the planet pass right between us and the star. So this one has one planet, and we see the star's brightness dip. And then we zoom in on another star, which has two planets. Unfortunately, they don't orbit correctly, and we will never see that star dip in brightness. So we think that star has 0. This one also has 3 planets, but that star never gets dimmer. So we do not know about any of those planets. Let's look at another star. This one has 3 planets, but only one of them is going to cross in front. We are going to think this star only has 1 planet. In order for the transit method to work, the planets have to be orbiting on the same plane that we are looking at the star at, so that they can cover up part of that star's brightness. Unfortunately, most planets probably don't orbit directly between us and distant stars. They might orbit like this, which means they'll never come between us and that star. So we probably miss most planets that exist. Even though we miss most planets that exist using the transit method, we still have 78% of all planets. Wait a minute, let's update that. We still have 76% of every exoplanet detection made using the transit method. So it is far and away the best way that we have to find exoplanets, even though we most likely miss virtually all of them. So what are some pros of this? You can determine the size, the orbital period, the distance from the star, the number of planets. You can figure out the size of the planet. If you know the size, you can probably figure out what it's made out of. Is it solid? Is it a gas giant? We found thousands and thousands of planets this way. What are some cons? Well, it's very tricky if there's more than one planet. It works best with telescopes in space, and everything has to line up just perfect. Otherwise, we're going to completely miss that planet and not know that it's there. I'd write some of this down. Now what I would like you to do is go back into your science journal, and where you wrote down what each of those 5 different methods was, I want you guys to draw a little sketch, some little picture that reminds you or represents those 5 methods. So we have taking a direct image, we have gravitational microlensing, we have astrometry, we have radial velocity, and we have the transit method. And here's an exit question for you guys. How does the study of exoplanets compare to the study of planets in our own system? How is it similar? How is it different? It's probably pretty different. What ways is it different studying an exoplanet than studying, let's say, Mars or Jupiter?